So good afternoon, everyone. Thank you very much for joining this final presentation of the AI for Health team from FruitPunch AI. So my name is Jennifer Dont. As Bram mentioned, I work at Mastro, and I had the great pleasure of guiding this team over the last few months. Although when I say guiding, it's kind of an overstatement. To be honest, I didn't really have to do much in the last few months, except sitting in on a meeting every 2 weeks where they showed their progress and their results. And I just had to say, well, that's really well done. So just to give you a bit of background, this project actually started already, not the project itself, but the idea in October, quite some time ago. I had to check my emails if that was correct, but at that time we received an email from Bram in our research group saying that they had some interested students who wanted to do an AI health related project, and we could basically do some propositions. And looking back, I was very lucky that they chose one of my projects at that time. Which wasn't the project that they will present today. It was a project related to dual energy conversion, also with deep learning, but something completely different. Unfortunately, I think on the day that they were planning to start, although all the administrative work was finished, we actually didn't have a single image to work on. Which sometimes happens with AI projects, but luckily we also had some other issues lying around, some other data that they could work on, and I have to say they were super professional and they just immediately switched to a topic they didn't initially choose, but in the end I think turned out really, really well, and I'm also very happy to see the results today and that they can present them to you. So I give the floor to the students who did basically all the work over the last few months.
Thank you for the kind words, Jennifer. If Jans can share our screen. Well, good afternoon, everyone. Thank you all for showing interest in our FruitPunch AI for Health project, covering to improve the automatic lung segmentations from X-ray images with the use of a generative adversarial network. My name is Meert van den Berg, and together with Jans van der Zande, I will present and discuss our methods and results.
You can just...
If everyone can mute their mics, it would be fine. Thank you. This AI for Health project is initiated by Mastro and aimed to optimize the current workflow of the radiology department at the Maastricht Universitair Medisch Centrum. This project fits the FruitPunch AI mindset, as FruitPunch aims to implement innovative solutions for complex issues affecting society. First of all, I would like to introduce you to our team. This team consists out of students from data science, AI, and medical engineering. A quick side note, this picture was taken during the only time we've been together as a team, but working online did not limit us during this project, and we were able to produce some promising results that we will gladly show you today. So now back to the project. The main goal of this project was to build a generative adversarial network that accurately segments the lungs in chest X-rays. This network will be employed in a bigger and improved workflow regarding COVID-19 classification. The current workflow involves 2 time points where a radiologist has to examine a patient, which is first to detect if there is a COVID infection, and in the later step, it's to further specify the severity of the infection. And you can imagine that this is a very time-consuming task to do manually, especially when there is a huge influx of patients that we've seen this past year with the COVID infection. And this can slow down the general care process, which is unwanted. And a way to support this process is to create a neural network that can help classifying these images and assist the radiologist in making their decision. And for this, the segmentation of the lungs is the first step for creating this classifier on lung diseases such as COVID-19. This ensures that the classifier is exclusively trained on lung tissue and does not get any features or other unwanted items from the image other than the lung. However, this is a challenging task, as due to the severity of the infections, the lungs are less clearly defined on the chest X-ray image. This is why conventional segmentation models usually fail, and it is expected that a generative adversarial network would perform better. A generative adversarial network can be summarized into 2 simultaneously trained neural networks, a generator and a discriminator. And in our case, we were working with the conditional generative adversarial network, which means that the input of the generator is an input image instead of some random noise. The generator is usually a known segmentation network that produces the masks, whereas a discriminator is a classification model that predicts whether a mask is true or generated by the generator. This has the added benefit of a check to see if the generated mask is looking like a real mask. The goal of the generator is to fool the discriminator. Therefore, they are in some kind of competition, and the goal during training is to find the equilibrium between these two networks. Before delving into the specifics of these models, I will first elaborate a bit more on the dataset itself. The dataset we've used for this study is a combination of 4 open source datasets of patients with either a form of pneumonia or COVID-19. In total, these sets added up to approximately 1,000 2D chest X-ray images. And from these images, we used 80% for training, 10% for validation, and 10% for testing. Some datasets provided ground truth masks. The masks included in the dataset had to satisfy a number of criteria. The most important one is that all masks needed to have smooth edges and follow the contour of the lungs closely, which you can see on these images on the right on this slide. For 2 datasets, we had to manually draw our own masks, as one did not comply with our criteria, and another dataset, the COVID dataset, did not provide us with any ground truth masks. And since the team is not specialized in this task, we consulted Mastro in some challenging cases. As we used 4 different datasets, it was important to apply some pre-processing. One dataset was characterized by having large areas of zero padding, which you can see on the right side. We removed these areas as they could affect the next 2 steps in the pre-processing. We standardized the images by their own mean and standard deviation in pixel values. If these black areas were still present, this would affect these statistics of the image negatively. Thereafter, we resized the images by setting the largest axis to 512 pixels and add zero padding to the other axis to make the images squared if needed. The difference between not removing the black areas and how we did it is visible in these images on the slide. Traced with pink, you can see in the top image the original image in the dataset, and in below you can find the image after we pre-processed it in our way that I just described. And you can see that the image to background ratio is higher, which is beneficial during training. Now that you have a bit of an idea about our input data, let's discuss the model architectures a little bit more. You might recall this schematic from an earlier slide, but I will now explain the training process more thoroughly. To update the weights from the GAN, first, the discriminator is trained on the set of real examples, which is the random input image with the real mask. And then the weights of the discriminator are updated accordingly. Thereafter, the discriminator model is trained with the input image and the generated mask by the generator. And then the discriminator has updated its weights accordingly to that training process. And then the discriminator is frozen during training. The weights of the discriminator are frozen during training so that the generator can be trained. And this uses the input from the output of the discriminator model and uses the input image and the true mask to further optimize that model. Once the cycle completes, the weights of the discriminator are unfrozen again, and the training starts with a new set of images. When zooming in into the generator, it consists of an encoder and decoder block combined into a UNet architecture. This UNet model first passes the input into the downsampling layers, which is the encoder side, until it reaches the bottleneck. Here the model is forced to learn a compressed view of the features of the image, and then this bottleneck representation is passed into the decoder set of the decoder layers from the model. There are skip connections you can see here on the bottom that help the model learn more fundamental features such as the lung edges. And these are passed from the encoder layers to the decoder layers directly in the corresponding level. And to be more specific, the model is built from 7 encoder and 7 decoder blocks. And every encoder block consists of a convolutional layer, conditional batch normalization, and a leaky ReLU activation. It downsamples the input and passes this through, and the decoder block upsamples the input from the bottleneck. The first part of the decoder consists of a convolutional transpose layer, a batch normalization, and a conditional dropout. And then it takes the input and concatenates it with the skip connections from the encoder. So those are the skip connections I mentioned earlier. And they also are followed with a leaky ReLU activation. When the input is pressed through all blocks, it is transposed one last time before it encounters the sigmoid activation, which produces the output. And this output represents the chance for every pixel to be lung tissue or not. And we put the threshold on 0.5 to binarize the mask. And the generator is optimized with the Adam optimizer. And therefore, we used a weighted combination of the binary cross entropy, which is outputted from the discriminator model, and the mean squared error, which is the error that's computed from the output mask and the ground truth mask. The discriminator is a convolutional neural network with a little less complicated structure. It's built up from 6 convolutional layers. And as input, it takes the input image and the mask that is generated, or that's either generated from the generator or is a ground truth mask. And it tries to predict if the input mask is the real mask for the input image or a fake mask generated by the generator. The structure of the model is that when the input is concatenated, it passes through the first convolutional layer, also with the leaky ReLU activation. And this step is followed by 5 more layers of convolution, batch normalization, and leaky ReLU activation. And finally, a sigmoid activation is used to classify the input mask and test the prediction if it's a real mask or a fake mask. To optimize the performance, the Adam optimizer with the binary cross entropy loss function was used. As the loss functions of the discriminator and generator fluctuate a lot during training due to their competitive nature, we have added a validation loss framework as shown on the slide so that we can keep track of model convergence. This validation loss is defined as a negative die score so that the loss would keep decreasing. And that is more intuitive to make sure that the model is still going the right way. And Jans will further elaborate on the die score when explaining the evaluation measures on the test set. And when the validation loss did not decrease for 5 times in a row, the training process was stopped to prevent overfitting. And the generator model weights were saved every time that an epoch resulted in the lowest validation loss thus far. In an attempt to improve our results, we also tried to increase our dataset with the use of data augmentation. And this entailed that for one original image, an augmented image was created. And this is done by generating a random value that picks a degree of rotation, translation, and the variability of the Gaussian noise. And this range of values for the rotation was between -15 and 15 degrees. The range for translation was between 0.05 and 0.15. And for the Gaussian noise, we used variability of 30. And all in all, this step doubled our data set. However, since our code used an array that loaded the entire training data set before entering a training loop, increasing the data set like this on the original 512 by 512 size was not possible with our GPU resources. So we tried downsampling the images to half a size. And this was feasible, but eventually this led to worse results than the original dataset in full size. So therefore, the results we will show you today are on the dataset without data augmentation. And I will now give the floor to Jans to talk more about our post-processing of the generated masks and an analysis of our results.
All right, thank you, Mirte. I'll take over from here. So while analyzing the results after training, we saw some inconsistencies in the generated mask. In the example on the left, you see some separated white areas that do not represent lung tissue, and other masks included some small black holes in lung tissue. So to overcome this problem, we used morphological operations. So we started with the opening with a kernel size of 5 by 5, and that was followed by morphological closing with a kernel size of 4 by 4. So it did affect the mask with poor quality, and it didn't not greatly affect mask with higher die scores. And for evaluation, we decided to implement 2 metrics as they assess different aspects of evaluation on the test set. The die score as an overlap-based metric, and the Hausdorff distance as a distance-based metric. So as Mirte mentioned before, she mentioned the die score. So what is this die score? This die score is a coefficient that measures the similarity between 2 sets of pixels, and is calculated by 2 times the area of overlap divided by the sum of the 2 sets of pixels. And as an addition to the evaluation of the generated mask, we also calculated the Hausdorff distance. And this Hausdorff distance defines the maximum distance between 2 sets of pixels. And in this case, we compared we used the ground truth mask and the generated mask, and then it calculated the max distance between those 2 masks. And then here are some plots about the results for model convergence. As you can see on the first image on the left, the training process of a generative adversarial network is very unstable. As you can see on the dice loss, at every step, it's very fluctuating. And in the second plot, you can see the mean dice loss for every epoch. And eventually, leaving us with a test loss equal to minus 0.4094 and a Hausdorff distance of 30.2 pixels. We also checked the model performance with different random seeds, and this resulted in a die score of, or a mean die score of 0.93 with a standard deviation of 0.001 and a Hausdorff distance of 30.2 with the deviation of 2.75 pixels. And this is shown with these box plots. The test set consisted of 99 generated masks for each trained model. As you can see, the die scores indicate that the models perform equally well, whereas the Hausdorff distance values show a broader spread and more outliers. The mean test Hausdorff distance values are approximately the same. And we also checked the performance with different trainer validation splits. And the model performance can be qualified by a die score of 0.95 and with a standard deviation of 0.002. And the Hausdorff distance for these models was equal to 29.72 with a deviation of 1.84 pixels. Also visualized with these box plots. In these box plots show the show that regarding the die-score, the models seem to perform equally well. The variation between the different test scans is smaller than looking at the different model initializations. The lowest die-score is around 0.65, and seen for one prediction made by model 5. Regarding the Hausdorff distance, one could notice more differences between the trained models. Model 4 shows the lowest mean value while having the most outliers. And here are some results of our visual inspection. On the left side, you see some generated mask with a higher die-score. They look very similar to the ground truth masks. And on the right, you see two examples with a low die-score. The first example is understandable to have a low die-score, since the borders of the lung tissue are not very clear. And for the second example at the bottom, the lines are clear, but the algorithm is not capable of generating a desired mask. We also have here 3 examples of the inter-observer variability. And this is all team members have drawn mask manually. And the pink squares show some important differences. For instance, in the left picture, there you see on the right lung are different. Here you see some members of the team have drawn the aortic arch differently. And for example, here, some included the heart. And at the bottom of the images, you can see the corresponding die-scores. These die-scores are the mean and standard deviation of all possible 10 combinations of team members. And these results are in line with the results of our trained model. So as you can see in these images, some of our data set, included some masks that contour masks that were not drawn correctly. This is a limitation of our study, since if these masks were drawn correctly, then the heart wasn't segmented as lung tissue, and our model does not include the heart tissue. So that would result in a higher die-score. And also our data augmentation was applied with images of 256 by 256. But we could, and therefore there's information lost, since we used images of 512 by 512. So for future studies, it's widely known that deep learning models such as GANs are very data-consuming algorithms and need large amounts of training data. So adding more data for our training process would be beneficial. Also, testing the model on a completely new data set will give insights about the generalization of the model. Furthermore, future studies could also do more extensive data augmentation. Our code had just one augmentation, which is an image with rotation, translation, and noise. It's also possible to do, for instance, augment an image 5 times based on one image with different values for rotation, translation, and noise. And that brings us to the conclusion. Although the best performance of our GAN seems to outperform a unit on the same task, it needs to be considered that with more parameter tuning of the units, similar results should be in reach. It is, however, interesting to see that our model scores higher than our own inter-observer variability. This gives rise to the question, how much better can the model possibly get? And to answer the question, an inter-observer variability check should be done with the real radiologist and that segmented the train data. And this would give a good baseline for our models to strive to. This can possibly be a suited tool for future clinical implications. Unfortunately, we did not have the chance to train our model on large quantities of data. Our expectation is that by increasing the data set and the quality of data, our model will increase in performance. And for now, it would be irresponsible to imply the actual clinical value of this model. And for the parameter tuning of our model, we found that only the batch size and loss function caused noteworthy changes. Also, experiments with the data augmentation suggest that a larger data set would result in a higher performance on unseen data. So we've come to an end of the presentation. We would like to thank Mastro and FruitPunch AI for this fun and interesting challenge. And thank you for your attention. If there are any questions, feel free to ask. Thank you.
Yeah, thanks a lot, Beert and Jans, for your presentation, and also Jennifer, of course, for the introduction. We have still some time left, so if you have any questions, put them in the chat or unmute yourself. That's also fine. And then the team will try to answer them.
I have a question.
Yeah, go ahead.
First of all, thank you for the presentation. It was interesting. So in the end, you said that an option would be to do the rotation to get data augmentation, right? But aren't all of the images you would work with in reality not rotated, but nicely horizontal? Would that still work then?
Yeah, we applied like small ranges of rotation, so between -50 degrees and 15 degrees. And therefore it still a bit helps us, or it's still in a range that is possible that it's also in the clinic, because especially in COVID cases, these chest X-ray images are made while the patients are in can be in their bed with all the a lot of cables and everything on top of them. And then it's also seen that sometimes the lungs are skewed to the left or right in the image. So in this case, this was applied with caution. Indeed, that with regular images, you would expect them to be vertically, but sometimes they can have a bit of switch. I hope that answers your question.
Yeah, makes sense. Thanks.
Okay. Thanks for asking, Vincent. I have one question from Chala. How does the performance compare to the studies done with regular image analysis methods?
Yeah, we have, it's always hard to one-on-one compare the results with other research, because there's another data set and other conditions while training. And what makes our data set special is that we have COVID cases in them, and usually the conventional methods didn't. But therefore we trained our, the generator was made out of a UNet, and we took that UNet and trained our model, trained that UNet model on our data. And what Jans mentioned at the end was that the results of our method were slightly better, but not that much of an improvement as we expected. But we think that if we have more complicated data in our data set, so increasing our data set with COVID cases and decreasing the pneumonia amount, the percentage in our data set, that then our GAN would be better than the other cases as well. But that was just a limitation of our resources we had in this study.
Okay, I hope that answered your question, Chala. I see it does. Great. Yeah, so great answer, Mirte. I think as well that your performance was great, and maybe comparing with some metrics, it might not outperform that well, but given the data and the vast diversity of the data you had, you did a really great job on achieving the same results as like a gold standard unit. So that's really impressive. I see for now no new questions have come in, but I do have one myself. The DICE score as an evaluation metric for me is quite intuitive, as it's like it ranges from 0 to 1, right? But the Hausdorff distance I'm not that familiar with. So you showed these box plots with the range of variability in the values of that Hausdorff distance. Can you maybe elaborate a little bit on how well I should or how I should look at these values, as to say?
Yeah, I can have a go again, but I don't know if somebody else wants to try. Yes, maybe somebody.
Maybe I can try. So maybe you can imagine that this is a ground truth mask and this is a generated mask. Then it takes the maximal distance between the two masks, and it's, I think it's for indices, right? So in our example, it are expressed in pixels. So if we have, I don't have. No. So these are pixels. So the median pixel value is around 20 for these Hausdorff evaluations values.
And it's indeed hard to make like for the DICE score, it's indeed between 0 and 1. But with the Hausdorff, it's more that you can compare it with the other. So like if the Hausdorff distance is smaller than another model that predicts, or lower than the other model, then you know that that model is performing better than the other one. So
okay.
It's not like you want the value to be as close to 0 as possible, but due to some noise we encountered, or that indeed, for example, the heart was segmented in the ground truth mask where our model predicted it without, then the Hausdorff distance is also a bit higher because the ground truth mask wasn't as we expected.
Yeah.
So that was limited in that factor.
Okay, well, that's clear. Thank you. I see we also have a new question from Luke. What if you added a high pass filter to the Gaussian noise? This is a technique we use in design when image editing to enhance details in an image. And then a disclaimer, I'm not a data scientist or engineer, so I don't know if this is applicable, but still, thank you for your question, Luke. And maybe the team can try to answer it for you.
Yes, I would like to answer this one.
Ah.
So I'll be honest, I had to look up what a high pass Gaussian filter was, but I'm seeing here that it is, I think it enhances the contrast, and we have not tried it, to be honest, but the thing is with a lot of these images, especially when there is a sort of pneumonia or if they are COVID infected, that it big parts of the lungs sometimes are very vague or are very hard to even see by a human eye what is part of the lung and what is, for example, part of the heart or aorta or anything. So enhancing contrast in that case would maybe take out part of the lungs where there would be a little kind of color difference. And also because you don't want the ribs or the rib cage to have too much influence on your imaging, we should try to give you a real good answer, but for now, I'm not sure if that would work.
Okay.
I had one question.
Yeah, go ahead.
You mentioned that batch size had a large impact on your results, and also because you also mentioned that the whole conversions process was so chaotic. It seems like an interesting parameter. So I was just wondering what batch size did you end up using for training your GAN?
Eventually, we trained with a batch size of 1 because that resulted in the best validation dice score, dice loss value. We also tried batch size of 2 and 4, but higher than that we couldn't go due to our resources in GPU. So,
all right. So you fed 1 image per step.
Yes.
Yeah. Okay.
And then like every image from the training data set was used during 1 epoch. So,
yeah. All right.
Yes.
Interesting. Yeah, because normally in maybe in GANs it's different, but you'd see batch size of 32, 64, but you couldn't go that high because then you need to, because each image is just too big. Okay.
Yeah.
Thanks.
Thank you for the question.
Yes, thank you, Milan. I see no new questions are coming in, so I will give everyone just a couple of minutes to come up with one, if you have any. Otherwise, we can move to the closing remarks of this presentation. But if you still have any questions, please don't hesitate.
Maybe it would be of interest also if they maybe explain very shortly what their hardware uses were. So the reason why you had a small batch size, you didn't have a very big GPU NVIDIA computer standing next to you, but you had some other resources that you used. Might be interesting to shortly explain that.
Yeah, we implemented it in Google Colab. So their free resources were used during this project. So that's it, I think. If somebody else
I think also, yeah, good to explain for this is because we, as Meert already mentioned, we met each other for the first time 3 weeks ago. So Google Colab was for us a nice outcome to be able to share the code with each other efficiently. And because we are all at home, for me, I'm just working on my MacBook, and I don't know what laptops the other guys have, but I didn't have any access to any GPUs, so Colab would provide us with this very needed processing power. But still, yeah, of course, because it's a free service, there were limitations. So you wouldn't always get the right or the best GPU available, or you would only be able to train your model for what was it, like 6 hours a day, and then would be kicked out. So those limitations were surely there, and I think if we had more access to better GPUs and more processing power, this would positively benefit our outcome as well.
Yeah, I think it's important to highlight is that the quality of your data was not excellent, the quality of your computational resources were not excellent, but despite that, you still have really nice results. So I think it's important to also mention that here. I see there's another question.
Yeah, so that's a great conclusion, Jennifer, to the hardware question. I see, I'm sorry if I'm butchering your name, but Min and Hele is raising her hand, so please speak up.
Thank you. It's Minentle. Yeah.
Excuse me.
Thank you so much for the presentation. It was really interesting. I just wanted to ask, it's not really a question directly at the presentation. So I recently joined FruitPunch, and I am interested to know, like, as the previous lady mentioned, Jennifer, she said your results are not that excellent. But they show some good results. These challenges or these activities, how does it work? Do you work? I know one of the challenges is with the Nederland Medical Center. Are these results used by the hospital for future reference, and like how does that contribute to the solving some contemporary solutions, say, in medical care?
Okay, yeah, good question. So more about the context of having these AF Health projects.
Yeah.
Maybe Jennifer, could I ask you to answer a question in respect to what is Masro going to do with this solution? And then I can add a little bit to why we are having these projects.
Yeah, definitely. So when Bram contacted us a few months ago, we could propose our own projects. And some of these projects really have clinical implementation very shortly in time. Some are more fundamental research, so they will not have immediate clinical implementation, but they're still, of course, very valuable because most of the time they are sub-projects of larger projects that we are doing in the hospital. So it's typically a very practical issue that we want another team to solve for us, but it's also an issue that we can clearly define what the issue is and what kind of solution we expect in a few months. And then, yeah, sometimes there's clinical implementation very fast. Sometimes it's more of a fundamental thing. But for example, for this project, it will be used in a bigger project that will have some clinical trials next year. So it will definitely be used in the clinic, this project.
Okay, very nice. Thank you.
Yeah, thank you for your question. I will give in my closing remarks some more additional info about the context of these challenges. So I hope to answer your second part of your question then.
I think it's also up to the team in the end what they choose, because we propose multiple projects, and I think we could indicate, is this a high-risk project with a high impact or a low-risk project with a lesser impact? And then, of course, it's up to the team what they prefer to do, and if they prefer to join more a fundamental topic or a more topic with clinical implementation.
Yeah. Let me have a look at the time. I see no more additional questions in the chat. Okay, well, if you come up with any, you are still free to ask. We still have like 10 minutes left or so. But it might be nice to give you some more information about AI for Health and our projects that we are having. So it was really great to see like the results of our first AI for Health project. It's nice that we have heard from Jennifer that these results will actually be used for a clinical trial later on in the clinic in Maaslo. But with our AI for Health vision, we are not intending to only make local solutions and solve local problems. We really want to scale up these solutions so everyone can access it and benefit from it. So that's why I want to ask you to, if you are interested about results of this project, please have a look at our socials, as we will soon be posting these results. So we will make the code available, the README files, a report even about how the methods that are used, results in itself. So a nice summary of this project. And if you then want to implement these results yourself, you are free to do so. So this way, FruitPunch AI is ensuring everyone can benefit from these very local AI for Health projects, which I think is really nice. And if you, after watching this presentation, have a feeling, oh, I would really want to be part of such a project myself, also have a look at our socials, because we will soon be posting about our third AI for Health project. There's currently already a second one running, but those results will be published in around a month or so. So stay tuned for that if you're interested in these kinds of projects. I will now drop in the chat a link to our FruitPunch AI platform, where in general you can find everything FruitPunch AI is organizing. So not only like presentations about the projects, but also when we are recruiting for new projects, when we are hosting a masterclass, when we're hosting a hackathon or a lunch lecture, everything that we do, you can find it on connect.fruitpunch.ai. So yeah, if anything of today interested you, please sign up for our platform. Then I see still no new questions have been posted, so I think we will end this meeting on some final notes that I want really to thank the FruitPunch AI team members, so everyone that's dedicated their free time to help us solve this challenge, and of course Maaslo for setting up this project, thinking about where we can make a difference in the clinic, and then especially Jennifer for then guiding this FruitPunch AI team to achieve these great results that we presented to you today. So if there are no further questions, I want to wish you all a good day.